In this part, we're going to introduce you to the derivative of a polynomial function. So let's consider the polynomial f of x equals x to the power of n. This is one of the simplest polynomials. We should be familiar with the graph of this kind of polynomials. Now, the derivative of a polynomial is very simple. It just follows a very specific rule. The rule is for the derivative, which we're going to note with a dash. So f dash of x represents the derivative of the function f, is going to be, bring out the exponent, n, to multiply x to the power of, take away 1 from the current exponent. So, for example, if the function was y equals x to the power of 5, the derivative of this function, y dash, is going to be 5 multiplying x to the power of 5 minus 1. That is 5x to the power of 4. If the function was y equals x to the power of 10, then its derivative, y dash, is going to be, bring down the exponent 10 to multiply x to the power of 10 minus 1. So the derivative would be 10x to the power of 9. It's very simple. The rule is, in general, bring down the exponent, multiply it by x to the power of n minus 1. Now you would ask, what if the function originally has a coefficient different from 1? So if you have a function that has a coefficient, for example, 2x to the power of 2, then what you're going to do is exactly the same thing, only that when you bring down the exponent, it's going to multiply the coefficient. For example, in this case, y dash is going to be 2 times the exponent, 2 times x to the power of 2 minus 1. So the derivative would be 4x to the power of 1. One more. Imagine this has a coefficient of 5 and it has a negative power of minus 3. The rule is still the same. Even if the exponent is negative or a fraction, you're going to use the derivative in the same way. The derivative for this function is going to be 5 times the exponent, minus 3, times x to the power of minus 3 minus 1. In this case, 5 times minus 3 would be minus 15, so there is a change in sign in the coefficient, but also minus 3 minus 1 is minus 4, so you need to be careful to add those numbers correctly. It works the same if it was a fraction. For example, y equals 2x to the power of a half, a square root. The derivative, y dash, is going to be 2 times the exponent 1/2 x to the power of 1/2 minus 1. And 2 times 1/2 is equal to 1. X to the power of 1/2 minus 1 is minus 1/2. Now what if the polynomial has multiple terms? For example, take the function y equals 3x squared plus 2x plus 1. In this case, you have to differentiate each of the terms independently and then keep them in the sum as you had them originally. What I mean by that is, in this case, y dash is going to be, first, we need to do the derivative of 3x squared, following this rule. That derivative is going to be 3 times 2x to the power of 2 minus 1. Now we need to add the derivative of 2x. X here has an exponent equal to 1. So when we do the rule, we're going to have 2 times 1, x to the power of 0. From here onwards, I may not write and show you x to the power of 0 because x or anything to a power of 0 will be equal to 1. It's not very common that somebody will write the exponent a 0 in the variable. And usually you would just say that the derivative is equal to 2 in this case. Lastly, you want to add the derivative of 1. Now 1 is a number, but I can write 1 also in terms of a power of x. 1 can be 1x to the power of 0. So being the exponent of x 0, the rule would be 0 times 1 times x to the power of minus 1. But anything multiplied by 0 is 0. So the derivative of 1 is simply 0. This is a very important result. For a constant or a number, the derivative is always going to be 0. And this makes sense because a constant function doesn't change, and the derivative is calculating the change or the rate of change. If the function doesn't change, then its derivative, it makes sense to be 0. So, simplifying the derivative for this polynomial is going to be 6x to the power of 1 plus 2. Let's do one more. Y equals minus 2x to the power of 5 plus 6x to the power of 3 minus x to the power of minus 2. It's a more complicated polynomial. It has the same 3 terms, but there is a few signs that are negative, so we need to be a little bit careful. What is the derivative of this function? So similar to before, we're going to start term by term. So y dash would be equal to, first we do the derivative of minus 2x to the power of 5. And that is going to be minus 2 times 5 times x to the power of 5 minus 1. Now we do the derivative of 6x to the power of 3. That derivative is 6 times 3, x to the power of 3 minus 1. And lastly, we do the derivative of x to the power of minus 2. And that is plus. Now I'm going to keep the minus as minus 1, the exponent, minus 2, and x to the power of minus 2 minus 1. Simplifying, y dash is equal to minus 10 x to the power of 4 plus 18 x to the power of 2 minus and minus is plus x to the power of minus 3. Before we do our first example, I want to point out something about notation. We have already introduced 2 ways to note the derivative. One is using the full name of the function f of x with the dash, so f dash of x. This one emphasizes the name of the function and the names of the independent variable. Just an extra detail, just so that we know that the rate of change is done with respect to x. And we also had y dash or y prime. This notation is brief. It doesn't name the independent variable, so we need to be aware about who is the change being measured against. So all the change is being measured with respect to x. Now there's one more notation, and that is dy over dx. And this notation, it names both the independent variables, and shows directly that the change is with respect to the variable x. And it is read dy by dx, or we simply say dy dx, the derivative of y with respect to x. All these 3 notations are interchangeable, and we are going to be using all of them just to refer to the derivative of a given function. Now let's do our first example. A ball is thrown upwards from the roof of a building. The vertical height of the ball from the ground in meters after 3 seconds is given by the function h of t equals minus 4.9 t squared plus 18t plus 50. The derivative function is given as h dash of t equals minus 9.8 t plus 18. A, find the initial velocity of the ball. B, find the time at which the velocity of the ball is 0. Interpret the meaning of this. And C, find the velocity of the ball at the moment it hits the ground. So we were saying that the derivative is representing the rate of change. So in this problem, when we're talking about distances and velocities, the derivative is representing the speed of motion and h is representing position, of course. So for A, find the initial velocity of the ball, we just need to know how fast the ball was moving at time equals 0. So at t equals 0, h dash of 0 is minus 9.8 times 0 plus 18. So h dash of 0, that's the initial velocity of the ball, v0, is going to be 18, and we're going to put the units meters per second. Now for B, we have find the time at which the velocity of the ball is 0. So they want us to say when is the ball at rest. At rest, h dash has to be 0. So we want to build the equation minus 9.8 t plus 18 equals to 0, and then we solve for t. So 18 is equal to 9.8 t. T is equal to 18 divided 9.8. That means t is 1.836. T is going to be 1.84 seconds. Finally, C, find the velocity of the ball at the moment it hits the ground. To know when the ball is going to hit the ground, we need to know when the distance from the ground is going to be 0 meters. So we need to find first at what time that happens. So that means we need to build the equation minus 4.9 t squared plus 18 t plus 50 equal to 0. And I'm just going to use my calculator to find that t is 5.5215. Now that I have the time, I need to know the speed at that time. So I'm going to evaluate h dash at 5.5215, and that is going to be minus 9.8 times 5.5215 plus 18. And that is minus 36.1107 to three significant figures. That's minus 36.1 meters per second.